optical theory. Welcome to the course Optical Communication. We start here the review of optical ray theory. Here, what is about we say the optical ray theory, in which we learn that a phenomena of a light travels through the medium. How that light waves are travels through a medium in a fiber optic communication. So we have the optical fiber, and in that optical fiber, your light is propagating through the fiber. And we have seen early in the morning, earlier lecture, that fiber has a core and a cladding. This one is about a core cladding here, and your light is propagating through this particular core. So our aim is about to learn that how light waves travel through this particular fiber or through this particular core. Okay, so that we are learning. So generally we say that a light waves has a velocity of what? 3 into 10 power 8. Okay, that is about a velocity. But in the case of a material or any medium, so all the light frequency not propagated with the same velocity. Okay, if you consider that. So because of what? That material have a denser cross section area, or they have a higher refractive index. Okay, they have a higher refractive index. Okay, so it is so based on that, the velocity of this particular light varying according to the refractive index. So means we say that if light is propagating through the free space, so that velocity doesn't change. But if you consider that a light travels in any material, so based on the refractive index of that material, light travels through that particular material. So then the velocity propagating through that particular material varies. Okay. So we consider here how that light ray is propagating through the medium, and we say that we have some particular source. Okay, we have some particular source, and light is propagating through that particular source. Okay, so in that case, when light is propagating through that particular region, this is nothing but a air. This light initially propagating through the air, then we have the fiber here. Means we have the material of this particular fiber. So we consider here. So if supposed to be we have a boundaries of these two different material, one is about a free space, another is about a fiber material. So means this one is about a boundary, and rays propagating from this air to this particular boundaries inside this particular fiber. So we learn here what will happen from the rays is propagating from one refractive index material to the another refractive index material. Okay, our aim is about to learn here the light rays. Okay, our aim is about to learn that light rays propagating from one medium to another medium. One medium to the another medium. So now that is about our aim is to learn here. That is how your light rays are propagating from one medium to the another medium. So here we say one medium is what? It has some refractive index. It has some refractive index. So we say supposed to be n1 here, and another is about to be n2. So what will be the difference of this particular n1 and n2 here? So if we say that right now we say that these materials have a higher refractive index and N2 has a low refractive index. Means light rays are propagating from higher refractive index to the low refractive index at the interface. So now supposed to be you consider that air, it has some refractive index and this particular fiber has some particular refractive index. So if you see that there is a difference of a refractive index, there is a difference of a refractive index. And in the case of if you consider that air, air has a low refractive index. So we consider one table. Okay. So I'll show you one table. So in which maybe there are the difference of refractive index is there. And according to that we consider that material. So what will be the refractive index for this particular material? So now consider here a material. Suppose I am saying that we have the material of what? Or you can say that air we have. Generally people are using word is about a vacuum. Okay. So it has the refractive index for the 1.0. If you consider that there is air, then it is not 1, but people are saying 1. It is about a 1.003. Or you can say that index of refraction for this air is approximately 1. Okay, it is not exactly 1. Okay, it's 1 here. Now, if you consider that refractive index of a water, or you can say that index of refraction, here we can say these are the material and this one is a index of refraction. So in that case, if it is a water, it has a 1.33. If you consider that ethyl alcohol, in that case, it has a 1.36. And if you consider that if used the silica, mostly this material, it has a 1.46. Or we have a silica glass fiber that is used in a fiber. It has a typical value of a 1.5. Or you can say it is about the approximately 1.5. So other material also available. So they have the different values of this index of a refraction. Diamond 2.02, 2.42. Then indium phosphide, it has a 3.21. Then only a silicon, only it has a 3.5. Okay, okay. So gallium arsenide actually, I, that is about a 3.35. Then silicon 3.5. Then indium, gallium arsenide, and a phosphide. Okay, it has a 3.51. If you consider that a aluminum, gallium arsenide, then it has a 3.6. And if you consider only a germanium, so it has a 4.0. So now these are the material. So now we say that there are the various difference in the refractive index. Now here air is a medium. If you see that this one is about air is a medium, and then a silica glass fiber. This is about your fiber. Now we transmit the signal from this particular source. This source means okay to this fiber. So in between that medium is the air, means light rays propagating from the air to the silica glass fiber. And in this case, air has a refractive index of 1 and a silica glass fiber has a refractive index of a 1.5. So there is a difference in a refractive index. Okay. Since there is a difference in a refractive index, so then what happened to the we say what happened to the interference. What happened to the interference at the boundary? Okay, that we have to learn. So at the boundary, what happened? Okay, that we have to learn here. So we start here with the review of optical theory. So in that case, we consider that a boundary of a instance here. Okay, we'll consider the boundary of a instance. Now this one is about, we can say, the boundary of a incidence, and for this particular boundary, this material has a low index, okay, low refractive index. Okay, we say it is about N2, and that material is a air now. And this material is what? High index, and this material is about a glass, and it has a value of a N1. Okay, now at this particular boundaries, if supposed to be any incident rays, if supposed to be any incident rays, now this is about a, we say it is about a incident ray. Okay, now if any incident ray is propagating, okay, if any incident ray is propagating from high refractive index to the low index, okay, this is about a high refractive index to the low index. So what will happen? So we need to consider the normal at this particular surface. Let's see, this is about a normal, because all this angle we need to consider with respect to the normal values. So now in this case, this one is about a angle incident rays. So expected value is what? It is to be propagating through this way, expected value. But it is not propagating directly. It will be just like exit ray. Okay, this is about the exit ray. Or I just draw likewise. This is about your exit ray. This is about incident ray. This one is about exit ray. And these values of angle, that is phi 2, and this one is about a phi 1. Now, generally, if you consider that a straight line here, if I consider likewise, if supposed to be there is no difference in the refractive index, then your signal will go likewise. Okay, signal will go. But no, there is a difference in the refractive index, so there is a slightly different. Okay, that angle changes. It's not go straight here inside that medium. It will slightly changes. So that's why it is a, that phi 1 is not equal to phi 2. If it is that there is no difference in the refractive index, then phi 1 equal to phi 2. So in that case, this will be, okay, this is the, okay, this will be the material. But here it has a difference in the refractive index, so that's why that material exists there. Okay, so this one, we consider that a refraction of your light from what? A high, okay, this is nothing but what? A refraction of a light rays from high index profile, high index to low index of refraction. Okay, so it has a high refractive index and a low index. Means this one is about, you have a material has high refractive index and it is propagating to the low refractive index. Now next case, a limiting case. In a limiting case, what happen? We supposed to be consider the same here always. Okay, so that you people are able to understand clearly. Now this one is about a medium we have. for this medium, we say N1, N2. Okay, medium is same. Right now we say it is nothing but air and it is nothing but a glass. And you know that for this glass, so it has a uh, refractive index high, and for air it has a low refractive. Now I just draw a normally. Okay, so that this is nothing but a normal here. Now we can say that this one is about a incident ray. This is about our incident ray. Now a ray is reaches here. Okay, ray is reaches here. In that case, due to the difference in this refractive index, okay, due to the difference in the refractive index, so at what should happen? Okay, so in that case, the condition is that if phi 1 is a large, we are changing the values here the phi 1. If we increase the phi 1, means likewise, if we increase the value of the phi 1 here, so in that case, at some particular point, okay, at some particular point, your light will propagating back. Okay, your signal will propagating back this way. It will be reflected back. So means everything is depending upon that what will be the reflection, that angle of a refraction here. Okay, this is about a, we can say that about a angle here. If that angle is a large, phi large, so at some particular point, so it will start reflecting back, and at some particular point, we supposed to be consider that, okay. So this is about your incident signal. Okay, this is about our incident. So we should know that what will be the values of a critical angle so that your signal will be reflected back. Okay, this is about a value. We can say it is about a critical angle. So your signal will be reflected, means light rays will be reflected from this particular boundary. The case is same. It is N1, this one is about N2. So we learn here a limiting condition for the reflection occur. Limiting conditions for what? A reflection occur. So now here is a critical condition for what? Your phi c. If that phi c, this, okay, phi is greater, then it will be reflected. If phi is smaller, if supposed to be here, so it will be refracted. Okay. So now simply I just draw again these three rays now. I'll draw a normal now. Okay. In one diagram, I will explain everything here. Now this is about you say that a incident ray. This one is about your incident ray. So it is supposed to be considered as a phi now. Now at some particular value of a phi, okay, at some particular value of a phi, signal will be what? It will be reflected here, or it will be exit here. Okay, so it will be exit here. Means it will be propagating through the medium. Now if I change the value of phi, now this one is about f of phi. So now what happened? That rays will be reflected back. Okay, that is about a condition. Means if I change the angle of incidence across this boundary, so then your signal will be reflected. That is about the exit ray. Okay, this one is about the exit ray. Now our aim is about to find out at what values of this phi I supposed to be say this in red color phi and blue color here now that rays. Okay, so now I'm saying here this one is about a phi 1 and this one is about a phi 2. Now at what value of a phi 1 and phi 2 at some particular condition your ray will be exit into the different matter. If it is a phi 2, so what will happen? It will be reflected. Here it will be refracted. This ray is refracted in this particular boundary. Okay, that is the body. Means it propagate in the another medium. That is called a refraction. Refraction. Okay, so ray is refracted, and here because of this particular ray, that is about the angle of phi is increases. So ray will be reflected. Now, at what critical value of this phi? Okay, at at what critical value of a phi, so that signal will be reflected. So our aim here in optical fiber, we need to consider that what critical value of a phi, so that your signal will be reflected back. Okay, signal will be reflected back. So means what? We say that critical value means what? We say that at this particular value is increases as per the whatever the critical value, so that your signal refraction and your reflection are depending upon the whatever the critical values there. Okay. So now our aim is about to learn here in these two rays that the critical values, so that your signal will be reflected. Now the same phenomena is used to understand that what will be the phenomena of a refraction of a signal and reflection of a signal. Okay, so we'll back again. Okay, to this particular point. Generally, we say that this one is about the index of refraction. This index of refraction, if you see that, it is depending upon that what will be the velocity and what will be the velocity of a medium. This one is the velocity of vacuum and this one is the velocity of a medium here. Okay, so this is about a incident. Right? So we can say that a refraction index, it is nothing but the ratio of velocity of light. Okay, it is nothing but a ratio of velocity of light into the velocity in a medium there. Okay, velocity of light into the medium. So we can say that is about a vacuum here, or we can say that is about a medium. So we can find out the index of a refraction. That is about a ratio. Now consider that the case is that we say here if that n2 is less than n1. Right now we are saying that n2 is less than n1. So in general we say that n1 is nothing but what we say it is about a glass material and it has a high refractive index. High refractive index. And a n2 is nothing but what? We say here it is a air and it has a low refractive index. It has a low refractive index. And this angle that we say that is about a phi 1. Phi 1 and phi 2 means what? This angle is about a phi 1 and this angle is about a phi 2. Phi 1 is nothing but a normal angle at the surface of interface here. Okay. So which surface we have? It has a high index. Okay. Phi 1 is a normal angle at the surface of interference. Okay. we have a, and we say a phi 2 is nothing but a normal angle in a lower index medium, in a lower index medium. Now that is about, we can say, a phi 1 and phi 2. So according to the law of reflection, or we can say that a Snell's law, n1 is equal to what? A sine of phi 1 is equal to n2 sine of phi 2. And that is called as a by Snell's law. Okay, that is called as a Snell's law. So we earlier say that n1 is greater than the n2. Okay, generally we say that n1 is greater than the n2. Then the angle of refraction. Okay, now here it is about a angle of refraction, which is always greater than the angle of refraction. Angle of refraction is always greater than, it's always greater than the angle of incidence. Okay, now how it is? Now this one is the diagram. Here, if phi 1 is the angle of incidence, phi 1 is the angle of incidence, and this is about a phi 2 is the angle of, we say, refraction. Now what we are saying here, the angle of refraction, this is about a phi 2 is the angle of refraction, and phi 1 is the angle of incidence. Okay, this is called a incidence angle, and this is called as a refraction angle. Okay, this is called as a refraction angle. Now we consider that a phi 1 and a phi 2 is nothing but what? A angle of incidence and a angle of refraction. So we say that angle of refraction is always greater than the angle of reflection. Now if consider that the angle of refraction, okay, that phi 2, okay, that is called as a angle of refraction, and that angle of refraction, if supposed to be, it is a 90-degree. Okay, if the angle of refraction, if it is a 90-degree, then what happen? If phi 2 is equal to 90-degree, what happen? Then that refraction angle, or we can say that, sorry, refracted rays, refracted rays emerges parallel. Okay, emerges parallel to the interface, emerges to the parallel to the interface. Now what is the meaning of this? Here I am saying that this is nothing but our boundary, and if supposed to be, I am saying this is nothing but a phi 1, and if that phi 2, this one is a phi 2, is a 90-degree. If it is a 90-degree, then a ray will be looks like a parallel to this particular interface. Okay, so means that ray will be looks like a parallel. Okay, if phi 2 will be 90-degree, then the refracted ray emerges parallel to the interface. Okay, so which interface? We say interface between the whatever the dielectric medium, or whatever the medium bit, two medium. This is about the angle of interface here. Okay, that is about a boundary or a medium. So that's why that angle of refraction, okay, so that's why the angle of refraction. Okay, so that will be if it is 90 degree, or if it is what we can say that suppose there is refraction here. So to get that a angle of refraction, so we should have the incidence angle is to be less than the 90 degree. Okay, incidence angle, this incidence angle, it is to be less than 90 degree. Means, what is the meaning of this? Now I supposed to be say that this is a boundary. If I increase the phi 1 here, so signal will be reflected back. If it is a 90 degree, I am saying incident angle is parallel. So it image is parallel here. Okay, at this particular one. So means what? Angle of incident should not be 90 degree. Or you can say that it should be a less than. Okay, less than the 90 degree. Or you can say that it should be a less than a 90 degree. Okay. Now generally some limiting conditions are there. So the limiting condition is what? At some particular value of this particular phi, okay, at particular value of phi, so they that refraction started, and that angle is called as a critical angle. So that is about a limiting case. Limiting case what? Limiting case of a refraction. Okay, where we have the angle of incidence, angle of incidence, which is to be called as a critical angle. That is called as a critical angle, angle of and that critical angle it is to be called as a phi c here. So that's why using the Snell's law, sine of phi c is equal to n2 by n1. Okay. So how it comes? So here earlier we say n1 is equal to sine phi 1 is equal to n2 sine phi 2. Okay. So we can consider that critical case, critical condition, sine of phi here. Okay. So in that critical condition, so we'll get that phi 2 becomes what we can say it is about a 0. Okay. Sine phi 2 will be a 0. So that's why sine phi 1 is nothing but a critical angle. And then sine phi 1 is equal to sine phi c is equal to n2 by n1. Okay. So that is called as a what we can say a critical angle condition. So in that case phi 2 will be a 90 degree, or we must say that that is a limiting case condition. In that case your signal will be reflected back from this particular boundary condition. So if we consider that based on this, or we can say that the angle of incidence, if it is greater than the critical angle, okay, if we consider that that angle of incidence, if it is greater than the critical angle, okay, angle of incidence is greater than the critical angle, then the light is reflected back. Okay, if that angle of incidence is greater than the critical angle, means what? We say that this one is about a phi, and if it is beyond this critical angle, it's likewise this one. If it is beyond this particular critical angle, so in that case, your signal will be reflected back. Okay, so when it will occur? So if we consider the that particular rays propagating through this medium, so they have the critical angle, that incidence angle is greater than the critical angle. Then your signal will be reflected back. even if that medium or that particular boundaries, it has a difference in the refractive index. Now say here we have the different refractive index n1, and this medium, it has a difference. Okay, even if there is a difference in the refractive index, if that angle of incidence is more than the critical angle, then all the signal will be reflected back. So that is called as a total internal reflection. This one is called as a total internal reflection. So okay, that is called as a total internal reflection. So generally we say that total internal reflection is 100%. No, so we will get that 99.9% of the total internal reflection, means high efficiency. Okay, total internal reflection for this, we can say here the high efficiency. Now, at a total interface occur, when it will occur, when we have the difference in the refractive index. Even if there is a difference in the refractive index, total reflection occur when the light is propagating, or you can say that incidence light is beyond this particular critical value, critical angle value. Then and then total internal reflection. Okay, so what happened here? The phenomena of a total internal reflection is what? That angle of incidence that will be exceed the critical value. Angle of incidence that will exceed to the critical values. If supposed to be, I am saying that if our rays are that angle of, it is about, this is about supposed to be incident ray, and in that case, if phi is small as compared to phi c, in that case, signal will be refracted. Okay, if it is below this, signal will be refracted. But if it is above this phi c, such signal will be reflected back. Refraction. This one is called as a refraction, and this one is called as a reflection. Reflected, refracted. Okay. So, so that is about a condition for the total internal reflection occurs at the interface between these two different material or two different dielectric material with a different difference in the refractive index values, and that happen when they have the angle of incidence of this ray exceeds the values of the critical angle, exceeds the critical values. Okay, so that's why the total internal reflection occurs. So we always consider that, so light is propagating, okay, light is propagating through the given particular medium. So if it has a sufficient angle of incidence or sufficient angle of reflection, then your light will propagating through the medium. Now inside a fiber, what happens? It has a core, or this one is about a core here. And so we consider that this one is a cladding now. This is about our fiber. Okay, this one is about our fiber. When a light, okay, for this particular fiber, this one is a core. Core it has a center now. Okay, that is about axis. Core has some particular axis now. So light rays, now if supposed to be we have the perfect fiber, okay, if we have a perfect fiber, so in that case your light rays are propagating. So this one is about a, okay, this one is about a core. This one is about a core, and this one is about a cladding. Okay. Now then, how it is looks like? I just, it's supposed to be, I draw a cross section of a fiber. If I cut the fiber, so it looks like this one is a core, and This one is the cladding. I just cut the section. And this one is the view of a fiber, optical fiber. Now, because of that variation in the refractive index, so generally core having the high refractive index and cladding has the low refractive index. So in that case, we say a core it is N1 and this is about N2. And for this particular fiber, N1 is greater than the N2. So in that case, what happens? Under some particular boundary conditions, your signal will that rays will come to the boundaries of this particular core, again refracted, again it will come here, again it will be reflected. So whatever the incident light is there, that will propagating and it will be reflecting here. So this one is about we say is about a angle of incidence. This one is about the angle of incidence. Based on the angle of incidence, your signal will be reflected here. Okay, based on this, signal will be reflected. So this is the phenomena used in a fiber throughout. Okay, throughout this particular fiber. So difference in the refractive index inside the fiber. So when light propagating through the fiber core, so it will be reflected. Means it will not propagating inside this particular cladding area. It will not go inside this particular region. Okay, if supposed to be it goes in this particular region, that is nothing but a loss here. But it is propagating only through the core itself. So what type of materials are used? So generally a silica core has a high refractive index. Okay, silica core has high refractive index. And we consider that a silica core and similarly for the cladding, so we consider that it should have a low refractive index material. So when that is about a angle of incidence, that phi 1 whichever we say here, that phi 1 is greater than the critical angle. Then and then your signal will be reflected. So now when we pass or when we propagate any signal, so we should know that rays, incident rays, okay, incident rays at this particular boundaries, they should match the condition or they should fulfill the condition of a total internal reflection.